Okay, good day to everyone. Today, this is another topic in power plant engineering, which is very helpful in your subject in power plant engineering. This time, we will discuss the OTTO cycle. So first, let us first define what is this cycle means. So this OTTO cycle is the ideal prototype of a spark ignition engine, or commonly known as the gasoline engine. So this cycle is named after Nicholas Otto. So that's a German engineer during the time of 1832 to 1891. Okay, so let us take a look at the diagram on the slides. So we will notice that this diagram is composed of two diagrams. The first is, of course, the pressure volume diagram, and the other is the temperature entropy diagram, or the TS diagram. Okay. So considering the first diagram, we will notice that this cycle is composed of four state points, as you see in the PV diagram. Say 1, 2, 3, and 4. Okay, 3 and 4. So at point 1, meaning the gas, after entering the cylinder, will be compressed to point 2. And then the addition of heat will be at point 3. And then expansion will be at 3 and 4. And then rejection of heat at 4 to 1. Okay. So, but what are those processes involved in this OTTO cycle? First, 1 to 2 is, as what I have said, this is compression. That is isentropic or adiabatic compression. So there is no such rejection of heat or addition of heat to this system. And 2 to 3, the process involved is constant volume heat addition. And then 3 to 4 again is another isentropic expansion. And 4 to 1 is constant volume heat addition. Okay, so if we now take a look at the TS diagram on the right side of the slides, 1 to 2 is isentropic. Okay, so we will notice that this line is perpendicular to the isentropic line here. Okay, and then 2 to 3 is constant volume. Another 3 to 4 straight line or isentropic, and 4 to 1 another is the constant volume heat projection. Okay, so let us now go to the analysis of the OTTO cycle. Okay, so if we consider the processes involved, or the process involved between 1 and 2, that is isentropic, we'll notice that the equation for S is equals to C is equals to PB raised to K is equals to constant. Okay. So, from the diagram, this PB raised to K equals to constant can be written also as P sub 1, B sub 1 raised to K is equals to P sub 2, B sub 2 raised to K. Or rearranging the equation, P sub 2 and P sub 1 is equals to B sub 1 over B sub 2 is equals to K. But what is the term involved here for the ratio of B sub 1 and B sub 2? So this is called the compression ratio, or designated as RK. Okay, so substituting now this RK from the above equation, so we can easily determine the absolute pressure at the end of compression as a function of P sub 1, or the absolute pressure at the suction condition, and multiplying it by the compression ratio raised to K, where this K is of course the isentropic constant. Okay, so again, considering the ideal gas equation, or the combined ideal gas equation. So for ideal gas equation, or the combined ideal gas equation, that is P sub 1, B sub 1 over T sub 1 is equals to P sub 2, B sub 2 over T sub 2. Okay. So, getting now the value of B sub 1 over B sub 2, that is P sub 2 over P sub 1, T sub 1 over T sub 2, and then substituting from the original equation here. So, and then getting the ratio of the T sub 2 and T sub 1, or the ratio of the temperature, and then that is T sub 2 over T sub 1 equals P2 over P1 raised to K minus 1 over K. Okay. So, another temperature in terms of compression ratio, that is T sub 2 over T sub 1 is equals to B sub 1 over B sub 2 raised to K minus 1, or simply T sub 2 is equal to T sub 1 multiplied by the compression ratio raised to K minus 1. Take note that the temperature at this point is in absolute. Okay. So, of course, if you use an ideal gas equation, you see to it that the pressure and the temperature should be in absolute. Okay. So, that is for the process of 1 to 2. Okay. So, another is for process 2 to 3. Okay. The process involved for 2 to 3 is constant volume process. Okay. For constant volume process, what are those term or other term used for this process? For constant volume, we sometimes call that as isometric process. Or sometimes we call that process as isochoric process. So, these processes, constant volume, isometric, isochoric, are all constant volume process. Okay. So, for constant volume process, so, by using the combined ideal gas equation and then eliminating the volumes, finally, this equation becomes P sub 2 over T sub 2 is equals to P sub 3 over T sub 3. Okay. So, next is heat added. Okay. Heat addition will happen in 2 to 3. Okay. So, for constant volume, the heat added is defined as the mass multiplied by the specific heat at constant volume multiplied by the change in temperature between 2 and 3. Okay, take note that the cycle utilizes air or utilize air as a working substance. Okay. And for air, the specific heat at constant volume is 0.7186 per or kilojoules per kilogram Kelvin. Okay. Next is for process 3 to 4. So this is again an isentropic process, only that the gas now will expand, or the product of, say, combustion will now expand from higher pressure at pressure 3 to pressure 4. Okay, so again, this process is isentropic, wherein the equation for isentropic, or the general equation, is PV raised to K is equals to constant. Okay, substituting now from the above equation, that is P sub 3, V sub 3 raised to K is equals to P sub 4, V sub 4 raised to K. Okay, so rearranging the equation, P sub 3 over P sub 4 now is equals to RK raised to K. Okay, so, or simply, the absolute pressure at 3 is equals to the absolute pressure at 4 multiplied by the compression ratio raised to the isentropic constant. Okay. Okay. So, again, considering the combined ideal gas equation, so this will become P3B3 over T sub 3 equals to P4B4 over T sub 4, and then getting the ratio of the temperature, or the highest temperature to the temperature at 4, that can be also, or T sub 3 becomes T sub 4 RK raised to K minus 1. So this is somewhat the same as with at T sub 2, or the process of the derivation are the same. Okay. Next is process 4 to 1. Okay. So this process is again a constant volume process, where again B is equals to constants, or constant rather. Or simply using again the combined ideal gas equation, and then eliminating again the volume at 4 and 1. Okay. So the remaining parameters now is equals to P sub 4 over T sub 4 is equals to P sub 1 over T sub 1. So, in this process also, 4 to 1, heat is also rejected. Okay. So, the rejected heat now can be defined as the mass, the specific heat at constant volume, multiplied by the change in temperature between 4 and 1. Okay. So let us now consider the difference between the two-stroke and the four-stroke engine. So we will notice that for a two-stroke engine, the cycle is completed in one revolution of the crank, okay, or flywheel rather. Okay, so take note that the cycle is completed in one revolution only. But for a four-stroke engine, the number of revolution required to complete the cycle is 2 revolutions. Okay. So that is for a four-stroke engine. Meaning, the cycle is completed after 2 revolutions. So, that is the difference now between the two. Okay? Another, we have the so-called piston displacement. If we take a look at the PV diagram again, the difference between the volume at 1 and the volume at 2 is of course the so-called piston displacement. Okay? Another is we have the so-called network. So this network is of course the difference between the heat added at point 2 to 3 and the heat rejected at 4 to 1. Okay, that is the network or the useful work. Okay. Another is the so-called thermal efficiency. Of course, thermal efficiency is the measure of how much of the energy input is useful or is utilized into a useful work. Okay, so that is thermal efficiency. So that is the ratio of the network and the heat added to the system. Okay. So substituting now from this original equation, the thermal efficiency now is equals to heat added minus heat rejected over heat added multiplied by 100%. Okay, substituting now the definition of QA at point 2 to 3. So, the definition of QA there is mass multiplied by the specific heat at constant volume multiplied by the change in temperature between 3 and 2. Same as with QR. Where that QR is also equal to M multiplied by the specific heat at constant volume multiplied by the change in temperature between 4 and 1. Divided by this by QA, which is MCB T sub 3 minus T sub 2. Okay, so eliminating now mass and the specific heat at constant volume. Okay, so that will now become T sub 3 or ET is equals to T sub 3 minus T sub 2 minus T sub 4 minus T sub 1 over T sub 3 minus T sub 2. Or that is equal now to, or considering that T sub 3 is equal to T sub 4 and RK raised to K minus 1. And T sub 2 also is equal to C 1 RK raised to K minus 1. Okay. And then substituting now T sub 3 and T sub 2, the equation now will become thermal efficiency is equals to 1 minus T sub 4 minus T sub 1 and then T sub 4 minus T sub 1 multiplied by RK raised to K minus 1 and then eliminating again T sub 4 minus T sub 1 over T sub 4 minus T sub 1. The final equation for thermal efficiency now is become or will become 1 minus 1 over RK raised to K minus 1. So we will notice that the thermal efficiency of the OTTO cycle is now only in terms of the compression ratio. So we will notice here that the higher the compression ratio, of course, the cycle is quite efficient. Okay? So, but take note that the compression ratio for an OTTO cycle is limited only to 8, something like that. Okay? So, the higher the compression ratio or higher than 8, maybe the cycle will become less efficient. Okay? So, let us now proceed to the network in terms of the initial pressure, volume, compression ratio, and pressure ratio. So, knowing that the work or the network is the difference between the heat added and the heat rejected. So, for isentropic process, the work is, of course, at 3, that is, okay, P3 minus B3 minus P4, okay, over K minus 1. So, this is for isentropic process. Okay. So, substituting now the pressure ratio, the compression ratio for the network, and then eliminating those parameters which is not needed, we'll notice that the work net in terms of pressure ratio, initial volume and initial pressure, and compression ratio as this. Okay? Work net is equals to Rk raised to K minus 1 multiplied by B sub 1 over K minus 1 multiplied by the initial pressure and then multiplied by the pressure ratio minus 1. Okay? So I think it is clear to everybody. Okay. Another, we have also the expression that defines the compression ratio in terms of the clearance volume. Okay? So, determining the compression ratio if clearance volume is given. So, that is Rk equals to 1 plus C over C. Take note that C is the clearance volume. Another now is the so-called mean effective pressure. So, you will notice that the mean effective pressure of the cycle of the of the engine is equal to the network divided by the piston displacement of the engine. Okay? Or simply that is QA minus QR over B sub 1 minus B sub 2. Okay. So, let us now proceed to the example so that we can apply all those formula there. Okay, so let us now take consider this problem. In an OTTO cycle, the pressure at the end of compression is 15 times that at the start. The temperature of air at the beginning of compression is 38 degrees Celsius, and maximum temperature attained in the cycle is 1950 degrees Celsius. Okay, so determine A, compression ratio, thermal efficiency of the cycle, and the work done. Okay, so let us take the isentropic constant for cold air as 1.4. Okay. So, how we are now going to determine the compression ratio? So, from the basic equation, so we know that the compression is isentropic. So, the equation now is the PV raised to K is equals to constant. Okay? So, substituting now from 1 to 2. So, P sub 1, B sub 1 raised to K is equals to P sub 2, B sub 2 raised to K. And getting now the ratio of the pressure, that is equal to the compression ratio raised to K, where the compression ratio now, substituting all the values, will become 6.9. Okay? Next is thermal efficiency. Okay. If the compression ratio are already known, so we can easily substitute that compression ratio from the efficiency or thermal efficiency formula. Okay? So substituting now 6.9 as the compression ratio, we'll notice that the thermal efficiency of the engine is 53.8%. Okay? Another is the work done. Okay. So, the work done, of course, is the net work. So, the difference between the heat addition and the heat rejected on the system. Okay. So, let us first define what is the temperature at the end of compression, since the highest temperature is already given. Okay? So, substituting now from the equation, T sub 2 will become 671.7 Kelvin. Okay? And getting now also the value of T sub 4, that T sub 4 is equals to 1029 Kelvin. Okay. So, anyway, this T sub 4 here is not needed anymore. Okay. So, we can also solve the heat added using the difference in temperature between 2 and 3 and multiplying it by the specific heat at constant volume. Okay, so substituting it now, the value of the heat added to the system is 1,115.3 kilojoules. Okay. So, knowing also that the thermal efficiency is equals to the net work over heat added. So, since we have now already a value for the heat added to the system, we can directly compute the work done by the system. Okay, so substituting it now from the equation, the computed value for the network is 600 kilojoules. Okay, so that ends our discussion today. Okay, thank you very much.